However, this is Christian and Jimmy Lee. We are going to present our work on revisiting the Deep Cox Mixtures for survival regression. Survival analysis is a crucial statistical method used widely in healthcare, engineering, and economics to predict the time until an event occurs, like patient survival. A key challenge is handling sensitive data where we don't observe the event for everyone. However, widely used models like the Cox Proportional Hazard model often suffer from poor calibration. Their predicted probabilities don't match reality, especially when the assumption of constant hazard ratios over time is violated. Even recent deep learning models, while better at ranking patients by risk, still struggle with predicting the exact probability of survival. This leads to significant real-world consequences like the 2013 pool cohort equations, overestimating risk for millions, impacting healthcare decisions. To address this issue, the Deep Cox Mixtures or DCM model offers a promising alternative. Instead of assuming a single risk structure, DCM models an individual survival as a mixture of k distinct cost models. It assigns individuals probabilistically to latent subgroups, each with its own non-parametrically estimated baseline survival curve. The final prediction is a weighted average of these subgroup survival curves. The models use a deep learning encoder to transform original covariates into latent representation, allowing it to capture complex nonlinear relationships. This representation then fits into two linear functions, one influencing the hazard within each cluster and another whose output while softmax determines the mixture probabilities for subgroup assignment. The model is trained using maximum likelihood estimation. Visually, a key success was reproducing the Kappa-Meier survival curves. Using the support data set, we observed shapes very similar to the original paper, confirming the ability to model non-proportional hazards, a core advantage over standard CPH. We compare our results against several baseline models, including the Cox Proportional Hazards CPH model, Deep Survival Machines, DSM, and Random Survival Forest, or RSF. And turning to the SEER dataset, we observed positive results, particularly for the minority group. A lower ECE in the minority group indicates better calibration, which is a positive sign for DCM's calibration on this dataset compared to the original paper's claims. Our CTD of 0.7356 was also close to the original DCM's value, indicating similar ranking ability. On the support dataset, our DCM reproduction showed weaker calibration, higher ECE, and lower ranking or CTD compared to the original paper's reported DCM metrics, often performing only comparably to baselines. Our reproduction study found the original paper was only partially reproducible. This was mainly because the original training code was unavailable, making it hard to match the exact implementation. Also, there wasn't a clear step-by-step guide for the training and evaluation process. These factors limited our ability to replicate the results precisely. We re-evaluated the models on an additional real-world clinical dataset, the German Breast Cancer Study Group. This is a historical dataset from a late 1980s trial for node-positive breast cancer containing profiles for over 600 patients with details on disease and treatment. Looking at the performance on this dataset, our DCM model achieved competitive performance when compared to other deep learning approaches like DSM and RSF using standard metrics. Notably, DCM showed great performance in ranking accuracy with a CTD of 0.6784, which was better than the traditional CPH models. Our DCM also maintained reasonable calibration with an ECE of 0.0745 on this dataset. These findings on the GBSG dataset help validate DCM as an accurate and practical alternative for survival prediction tasks in real clinical scenarios. Thank you very much.